Hello everyone, my name is Austin Rovinsky, and I'm Assistant Professor at New York University. This is the introduction to an online mini-course on physical design databases. Just as a disclaimer before we get started, this course is being released in summer 2024, and so it could get slightly stale as time goes on and the underlying software changes. But I have designed this course to hopefully focus on the more foundational elements, which should be stable for a long time. So what is this course about? If we simply break down the title, first, it's an introduction. This course will cover the basics, but there's still a lot of material not covered, and much to experience on your own. Second, it's about physical design. This is the process of physically implementing a chip. Think of every step involved in taking a hardware description language like Verilog and turning it into a chip layout file, which then gets sent to the foundry for manufacturing. Third, it's about databases. A database is simply an organized way to store data. Tying it back to physical design, we're going to be looking at how all of the important physical design information gets stored into a database and how you can access it. In this course, we're going to focus specifically on the physical database used in the OpenRoad project, which is called OpenDB. So why are we even concerned with physical design databases in the first place? Why learn this? Well, today, all chip design is done using software of some kind. Some of it may be to simulate your chip so that you can have high confidence it will work when you send the design to be manufactured. Much of it, particularly for digital designs, will be software algorithms to automatically implement and optimize your chip. For both of these cases and more, a way to represent your chip in software is particularly important. You need it to be able to represent the logical description of your circuit as well as the physical description of the circuit. Then, these software algorithms can use the information stored in the database to perform implementation, optimization, simulation, and more. So, if you want to get involved in electronic design automation, which is the design of these algorithms, understanding how to use databases is really the first thing that you need to do. This course does have some prerequisites, but they're fairly light. If you've completed 1 year of an undergraduate electronics engineering program, you probably have the foundation that you need in order to take this course. If you haven't, you can look at the course website or in the description of this video for some resources which should help you get up to speed and take this course. After taking this course, you should be able to understand what is a physical design database, what information does it contain, and why is it useful. Be familiar with accessing database structures so that you can create, read, write, and modify database objects. Use the database as a substrate to create your own EDA algorithms, and establish a strong foundation that you can start to contribute to the OpenRoad project or to create your own tools and algorithms based off of OpenDB and the OpenRoad platform. This course is structured as 14 mini lectures, with this being the first one. Each lecture is under 20 minutes and is designed to be very digestible. Additionally, there are 2 lab assignments that are included as part of this course. These assignments are designed to provide hands-on experience with using OpenDB for some basic design tasks. You can find the assignments on the course webpage, which include the assignment prompt, scripts for checking the correctness of the assignment, and also an instructor solution for the problem. For the best experience, I recommend not looking at the solutions yourself, at least until you've implemented the solution and tested it. Here's a syllabus of the lectures in this mini course. This video is an introduction to the course. Next, we have circuit taxonomy, which begins to define important terms when talking about how to describe the circuit. It's very important to make sure when we discuss these technical topics that we use the precise language so we can describe just the right thing. Next, I'll discuss a few industry standard file formats for storing information about semiconductor technologies. In particular, we'll discuss the Liberty, LEF, and DEF formats. The next 2 lectures will be about the OpenDB application programming interface, or API. We'll take the information from lectures 3 and 4 and then discuss how OpenDB represents the most important properties on a class-by-class basis. Lecture 7 is about the OpenSTA adapter. Just to give a little bit of foreshadowing, OpenRoad actually has two databases under the hood, one for physical information and one for logical information. I'll describe how that came to be and how to navigate the transition between the two when needed. Lecture 8, we start getting more hands-on. This lecture will be about how to download and compile OpenRoad software yourself so that you can start getting hands-on with the code base. The next two lectures will be about how you can create your own tool within the OpenRoad framework, and then how you can access it using the ODB interface and do something interesting with it. Lectures 11 and 12 will be about how you can turn your C++ code into something that can be used in a Tcl or Python script that an end user and not a developer would use. Lecture 13 will cover some advanced material on how to modify OpenDB and add more functionality to it. And the last lecture will be a brief overview on the current tools in OpenRoad and what they do. This will be useful if you want to jump in and start modifying and or contributing to the codebase of any of the OpenRoad tools. That's all for this lecture. I'd like to take a moment to thank Nordtech, who provided the funding to make this mini course possible, and thank you for taking the time to watch it. I'll see you next time.